Okay, let's look at some more freaky properties of water. We talked about the bent molecule, the hydrogen bonds, the high heat capacity, the high boiling point, melting point, universal solvent, and so on. Density of water also behaves weirdly beyond a certain temperature. Density, of course, is mass per unit volume. So high density, like iron or stone, means a small piece of iron or stone will be very heavy compared to, let's say, a piece of chocolate, which is not very dense. Density of water, like most substances, increases as temperature decreases. Remember, temperature is the kinetic energy of the molecule. So as you decrease the temperature, the kinetic energy decreases, so they pack closer together. So per unit volume, it will increase the number of molecules and the mass, right? So that's thermal contraction, shrinkage of most substances as you cool the temperatures. Except that water begins to behave very strangely when you go beyond 4 degrees centigrade. Remember that the molecules are bent and they have these hydrogen bonds, so they arrange in a certain way. As you cool them, they begin to pack themselves to maintain their hydrogen bonds, satisfy the polarity, remembering water is a dipolar molecule. So from 4 degrees centigrade to 0 degrees centigrade, the density of water actually decreases as the temperature decreases instead of increasing like all the other substances. This is a very unique property of water. So ice, which we will see in a minute, as actually we saw before, in fact, the molecules get organized very nicely into these hexagonal shapes, which actually increases its volume per unit mass. So ice actually becomes less dense than liquid water because of this changes in molecular packing, and the water expands as it freezes. And you probably know this very well. If you have put a bottle of milk or a cold drink in the freezer and forgotten it, then the water in the drink expands, the water in the milk expands as it freezes and can explode and break the bottle that it's in, right? This is something that you observe in the ocean as well, right? Glaciers in the ocean float, sea ice floats. What's the consequence? Well, one of the biggest consequences that we can think of is that if the glaciers were not floating and they sank to the bottom, then we wouldn't have the Titanic crashing into a glacier and that big tragedy. On the other hand, we also wouldn't have this super hit movie Titanic, right? Wow, that's just a joke. Water density and temperature, you can see here we are going from 20 degrees down to minus 2 degrees centigrade, or 68 degrees Fahrenheit down to 28.4 degrees Fahrenheit. The green curve here is for most normal substances. As you cool the temperature, you would increase the density to continue to increase. Whereas water, it does show some increase in density as you cool the temperature. You can see at 20 degrees it's still water, and the molecules are still moving very freely, but there is the hydrogen bond, so some of them are well organized, but some of them are floating around. As you go down to 15 degrees, more of the molecules are becoming well organized into these hexagons. And when you reach certain temperature at 4 degrees centigrade, you can see that the decrease is already beginning to reduce. So water is not linearly decreasing, it's a non-linear change in density as you cool the temperature. And at 4 degrees centigrade, it reaches its maximum density of 1 gram per centimeter cube, right? On the left here on the scale you have density in grams per centimeter cube. So point C here is the maximum density of water at 4 degrees centigrade. You can see the molecules are pretty well organized, multiple hexagons are getting connected, the kinetic energy of the molecules is decreasing, hydrogen bonds are getting stronger, and the polarity is being satisfied by organizing into these very nice structures. At 2 degrees, the density has decreased to 0.9999 grams per centimeter cube, and at 0 degrees, as ice is formed, the free floating molecules have pretty much disappeared, and ice is packed very nicely into these beautiful shapes. In fact, snowflakes, if you look at them, if you get a chance to look at them, they will have these very nice beautiful structures. So this beautiful structure increases the volume. So the packing is now such that the mass is being arranged in a larger volume. So you are going to decrease the density and you reach the minimum density at 2 degrees centigrade. We will see later on that as we add salt to water, arranging molecules so nicely becomes a little bit more difficult. So the density change, freezing point, etc. will change if you have impure water or salt in the water. Okay, so water density of course also depends on pressure. Increasing pressure or adding dissolved substances decreases the temperature at which the maximum density occurs. So it won't occur at 4 degrees, but it will occur at a different temperature. Dissolved solids also reduce the freezing point of the water. This is very common. If you lived in countries where there is snowfall, then you know that as soon as there is forecast of snow, trucks will come along and start putting salt on the streets, basically to raise the freezing point of water or snow that may fall, right? Instead of freezing at 0 degrees, you hope that it will not freeze as quickly, and you put salt. Of course, a lot of salt put in for snow conditions ends up in groundwater, in lake waters, and so on, and there are other problems created by that. Nonetheless, adding salts changes the boiling temperature, the freezing temperature, the density at which maximum, the temperature at which maximum density occurs. So salinity is basically the total amount of dissolved solids in water, which also includes dissolved gases, but it excludes dissolved organic matter. We'll see later on that there are a lot of dissolved organic matter in the seawater that is not included in salinity. So the ratio of mass of dissolved substances to the water itself is called salinity, and we think of water, seawater, as containing salt. Salt is NaCl. Well, most of it is NaCl, so chloride Cl minus is 92.2 grams. If you take 1 kilogram of water, 1,000 grams of water, only about 34.5 only about 35 grams is salts. Okay, so very small amount, but nonetheless, out of that 35 grams of salt, almost 19 grams is chloride. The rest is sodium, sulfate, magnesium, calcium, potassium, and others. So the typical ocean salinity is about 35 parts per thousand. So you can see this, the symbol here. Percentage is this slanting dash line, whatever we want to call it, with 1 0 on either side. That is parts per 100. You add another 0 below, that makes it parts per 1,000. So we look at salinity as parts per 1,000, which makes it easier than parts per 100. Instead of percentage, we look at salinity as parts per 1,000. So salinity makes for lots of interesting things. It plays a big role in biology and so on. All the organisms that live in the ocean have to worry about salinity for their water balance, for absorbing nutrients, for getting rid of waste, and so on. That depends on osmosis. So later on we'll learn what osmosis means. Okay, so density of water, another weird property. Add salt, then it gets weirder.